Now in this video we introduce you the Mohr circle and the application of a Mohr circle that is used to find out the principal stresses. So principal stress and the maximum shear stress are the main important concept in the theory of failures. So let's start with here 3D state of a stress. Maximum 3D of state of a stress consists of the 6 variables. One is sigma x, that is the normal stress along the x-axis. Sigma y is the normal stress along the y-axis. Sigma z is the normal stress along the z-axis. Then we have shear stress acting on the plane xy. Then we have shear stress acting on the plane xz. And we have shear stress is acting on the plane yz. The shear stress tau xy is same as equal to the shear stress tau yx. The shear stress zx will be same as equal to shear stress xz, and the shear stress yz is same as equal to zy. So they are one and same. So we'll draw here the 3D state of a stress using the three-dimensional cube, and then we draw the 6 stress element on the cube representing sigma x, sigma y, sigma z, tau xy, tau xz and tau yz. So let's consider our three-dimensional state of a stress by using a three-dimensional cube. So we'll set up our x-axis, y-axis and z-axis. So let's say this one is our x-axis, this one is our y-axis, and this one is z-axis. Actually I have to show these 3 axes at the center, but since I have to show the 6 stresses, so I have shifted it to the origin. So don't get confused. It is exactly at the center of the cube. So this face is perpendicular to x-axis. So you have to show the stress sigma x, which one is a normal stress. Normal stress is basically defined as a perpendicular to the area, and we'll show it outward. That will be the normal stress. So this one is representing the positive value because we are on the positive face of x-axis and is directed towards the positive of x-axis. The top plane is perpendicular to y-axis, so this one is representing the normal stress equal to sigma y, and this front face is perpendicular to z-axis, so we can show here the normal stress outward. So this one is outward arrow is representing the normal stress along the z-axis equal to sigma z. Sigma x, sigma y, sigma z, each of these stress are perpendicular to x face, y face and z face. And above the shear stress, the force and the area are parallel. So on this face it will be x face, so we can show the 2 shear stress. One is tau xy and second is tau xz. Tau xy, it means that we are on the x face and directed towards the y axis. So we are on the x face and directed toward the y axis. So this will be the shear stress equal to tau. First you have to write down on which plane, that is equal to x, and then you have to write down the direction in which it is directed. So this time it is directed to y. If you are on the same phase but you are directed towards the z-axis, then it will be again representing the shear stress. The plane is x but you are directed toward the z-axis. As we know, the tau yx and tau xy is same, so this plane is basically y plane. On this plane I will show the arrow parallel to the y plane but directed toward the x. So basically you have to give the first suffix equal to y, then you have to give the direction equal to x. So we have tau yx is same as equal to tau xy. And the second arrow you have to show along the z. So we are on the face y. So this value will be same as tau. First suffix you have to give for a plane that equal to y. It is directed toward the z. So you have to write down this value as tau yz. And if you are on the z face and you are directed toward the x, so this arrow represents the shear stress tau. We are on the z face and we are directed towards x. So this value of tau zx is same as equal to the tau xz. And you are on the same z face but you are directed toward y, and this arrow is parallel to the plane, so it will represent the shear stress tau, and we are on the z face but directed towards y. So these two values are one and same value. So this entire information we can write down using the stress tensor that is in matrix form. So we have stress tensor T is given as, first here you will make an entry for the normal stress along the x direction. So this one is a diagonal entry in the stress tensor sigma x, then we have sigma y, and then we have sigma z. Then the on x phase we have tau xy and tau xz. Tau xy is same as equal to tau yx, so I will write down this is same as xy, and this value will be equal to tau yz. Tau xz and tau zx is same, so this value is same as tau xz. This is tau yz is same as tau zy, so we'll write like this. So basically there are only the 6 elements in the 3-dimensional state of a stress. But in the maximum cases we have only the 2-dimensional state of a stress. So if you observe the same 3-dimensional state of a stress along the z axis, then what you visualize will be the 2-dimensional state of a stress. In the 2-dimensional state of a stress, no component along the z will come, so only 2, that is the value of sigma x, sigma y and tau xy. So this one is representing the x-axis, this one is y-axis. So this one we are right now discussing the 2-dimensional state of a stress. So let's represent here the sigma x and sigma y first. Sigma x is perpendicular to the x face, is going outward, and sigma y is perpendicular to the y face, is going outward. So this stress is nothing but the normal stress along the x direction, and this stress is nothing but the normal stress along the y direction. And if you are on this face, which is perpendicular to x-axis, and if we show the arrow directed toward the y, this will represent the shear stress equal to tau xy. And if you are on the y face directed toward x-axis, that is also representing the shear stress equal to tau xy. For the state of a stress, the summation of the forces must equal to 0, so you have to show the complementary shear. When you are showing the complementary shear, then always remember the summation of fx must equal to 0, summation of fy must equal to 0, and summation of moment above the point O must equal to 0. That is why sigma x is shown on the right side, then you have to show in the opposite side. Sigma y is shown vertically upward, then you have to show it downward. This arrow of a shear stress is rightward, you have to show it leftward. This 2-dimensional state of a stress is also called as the plane stress. So when you consider the stress on one surface are equal to 0, then it is called as plane stress. Thus this time I have taken the value of sigma z equal to 0 as well as tau zx, which is same as equal to tau xz is equal to 0, and tau zy is same as equal to tau yz equal to 0. But this is not compulsory that you can make sigma z 0. You can force the value of sigma x equal to 0, tau xy equal to 0, tau xz will be equal to 0. Then we have a 2-dimensional stress will be along the y and the z direction. Likewise, we can force the value of sigma y 0, tau yx 0 and tau xy 0. So the major purpose in looking at the stresses on different planes is to determine when a stress state produces failure. Failure of a material is complex, and the solid understanding involves the knowledge of both the material science and the mechanics. Mechanics of material and the stress transformation in particular are needed to determine the combination of the normal and the shear stresses at which the failure in the same material would occur. To calculate the value of the maximum principal stress and the maximum shear stress, we have to follow the sign convention, because we are using a formula for sigma max and sigma minimum as sigma x plus sigma y by 2 plus minus under root of sigma x minus sigma y by 2 whole square plus tau xy. So you have to put the proper value of sigma x, sigma y and tau xy so that we can find the exact value of sigma max, sigma minimum, that is the maximum normal stress, minimum normal stress and the maximum shear stress. So you have to understand the sign convention here. So let's consider here a two-dimensional state of a stress, and we have set up our x and y axis. So rule that we are going to discuss is same for both, that is a normal stress as well as shear stress. So both the normal stress or the shear stress will be positive value if it acts on the positive phase. Positive phase means from this coordinate system we'll call this one as a positive phase, or this one is called as positive phase. So this one is representing the positive phase, as well as this one is also representing positive phase and pointing to the positive direction of axis. Positive direction of axis is this axis. So this arrow is on the positive phase and is directed to the positive of x axis and is perpendicular to x phase. Whenever perpendicular, it will represent a normal stress that equal to sigma x. So if any arrow is pointed outward, will be taken as positive value. And if we are on the positive phase of y and the arrow direction is same as positive direction of y and is perpendicular to y, it will represent a normal stress that equal to sigma y. For this arrow, which one is on the positive phase and pointed toward the positive of y axis, so this value of the shear stress is taken as positive. So here sigma x, sigma y and tau xy all are taken as positive values. So whatever the calculation you do, then you have to represent the state of a stress as sigma x positive, tau xy positive, sigma y positive. Similarly, if we are on the positive y phase and we are directed toward the positive of x axis, in that case this value of the shear stress is taken as positive. So all these value here, the normal stress and shear stress are positive value. Secondly, if we are on the negative phase, that is this phase is negative and this phase is negative, then the shear stress and the normal stress is positive if it act on the negative phase, that is this phase or this phase, and is pointing to the negative direction of axis, that is downward or leftward. Then negative and negative will be the positive value. Like this phase is a negative phase, and on negative phase we are going to the negative of x axis, so this value of sigma x is taken as positive. Is positive, not negative. Negative into negative is positive. And this arrow is on the negative phase and is going towards the negative of y axis. So negative and negative will become positive. So this value of sigma y you have to take as positive value. Now about this shear stress is on negative phase and is going to the negative of x direction, so will be taken as positive. This one is same as our tau xy. And if you are on the negative phase and you are directed toward the negative of y axis, so this value is also taken as negative and negative as positive. So all these stresses that we have shown here are representing here the positive value. A normal stress and the shear stress is positive if it acts on the positive phase and pointing toward the positive direction, or otherwise. A normal stress or the shear stress is positive if it acts on negative, that is this phase and this phase, and is pointing to the negative direction, that is negative of x and negative of y, then again it is taken as positive. So you have to strictly follow the sign convention in two-dimensional state of a stress. So given state of a stress is in the xy axis, that is called as the plane stress. If this element is rotated about the z axis, which is perpendicular to the plane, in that case the value of sigma x, value of sigma y and the value of tau xy will change. So I am showing you the machine member here. Forget about the loading. If you consider this plane, then we have different value of sigma x, sigma y and tau xy. If you consider this plane, then we have different value of sigma x, sigma y and tau xy. As the plane will go on changing at different angle, we have different value of the sigma x, sigma y and tau xy. So this element is rotated about the z axis and counterclockwise rotation is taken as positive. So if the given element is rotated about the z axis, we can find out here the normal stress and the shear stress on different plane. It may be possible here that at certain value of theta, the value of tau xy will be 0 and the sigma will be the maximum value. So for a particular angle theta, if the value of tau xy will be equal to 0, then whatever the normal stress will be there, will be called as the principal stress. Suppose this state of a stress is rotated in an anti-clockwise sense at a particular angle equal to theta. Now this value of theta can be anything, but on this principal stress, we have axis of rotation will be changed as x prime, and this axis will become y prime. And given state of a stress, only the normal stress will exist and the shear stress will be 0. That is, this value will be sigma x prime will be called as sigma 1, which one is the maximum principal stress, and sigma y prime will be called as sigma 2, which one is minimum principal stress. And for this element, we have shear stress tau x prime y prime will be equal to 0. And this value of principal stress we can calculate as sigma 1 comma sigma 2 is equal to sigma x plus sigma y divided by 2. You have to take the plus and minus sign. One value will give you sigma 1, other value will give you sigma 2, under root of sigma x minus sigma y divided by 2 whole square, plus we have tau x y square. So the value of sigma 1 and sigma 2 are the maximum and minimum. What we call these are the principal normal stresses. So this will happen at a particular angle equal to theta. That angle is called as principal plane angle. So this plane angle will be equal to theta p is called as a principal plane angle. And we can calculate the value of principal plane angle using a relation tan of 2 times of theta p is equal to tau xy divided by sigma x minus sigma y divided by 2. So 2 will come in numerator. Geometrically there are two answers of this solution, and therefore we have one is the major value and other will be minor value. So it is compulsory for principal plane the value of shear stress must equal to 0. But again you rotate it by certain angle, then it is observed that the value of the shear stress will be maximum. So this angle will be different than the first angle. Let's call it as theta prime, temporary. Basically it is called as a plane of a maximum shear. And for this one the tau will reaches maximum value, that is we have tau xy y prime will be equal to tau max. But at this angle the value of sigma x prime is not equal to 0 and the sigma y prime will not be equal to 0. Whereas in the case of the principal plane the value of the shear stress must equal to 0. This value of tau max we can calculate using the relation. So we have maximum value of the shear stress tau max will be same as the difference between the two principal stresses, that is sigma 1 minus sigma 2 divided by 2. This is the one way you can calculate, or this under root sign itself represent the maximum value of shear stress. So we have plus minus under root of sigma x minus sigma y divided by 2 whole square plus tau x y square. So when the normal stress will reach the maximum value, it means that the shear stress will be equal to 0. But this is not true. When the shear stress will be maximum value, it doesn't mean that the normal stress is equal to 0. That is not always true. So you are able to calculate the value of the principal stress, that is the principal normal stress, using the equation sigma x plus sigma by 2 plus minus under root of sigma x minus sigma by 2 whole square plus tau xy square. And you can calculate the value of principal plane as tan of 2 theta p is equal to 2 times of tau xy upon sigma x minus sigma y. Similarly, you can calculate the plane of maximum shear, which is represented by theta s. Just the reciprocal of this equation is sigma x minus sigma y divided by 2 times of tau xy, but this one is negative. So this one is representing the slope m1 and this one is representing the slope m2. It means that the 2 times of principal plane, that is 2 times of theta p, and the plane of maximum shear, that is 2 theta s. These two planes are separated will be by angle equal to 90 degree. That is, we have m1 and m2, the product will be equal to -1. Whenever we have the product of two slope is -1, they are orthogonal to each other. So the difference of angle between 2 times of theta p and 2 times of theta s, So this difference is always equal to 90 degree. Or we can say the difference between theta P and theta S is always equal to 45 degree. So if you know the principal plane 1, then you can calculate the theta S just by adding the 45 degree. It can be plus 45 or minus 45. Next is that the maximum shear stress we can find out either sigma 1 minus sigma 2 by 2, that is same as equal to under root of sigma x minus sigma y by 2 whole square plus tau xy square. This information we can do very quickly using the Mohr circle. So this time I will introduce the Mohr circle first. The sign convention we introduce. Later on we'll show you how to draw the Mohr circle and how to find out the maximum value of the principal normal stress, the maximum shear stress, the principal plane angle and the plane of maximum shear. The video you are watching is from the app, which is the Mohr class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.